Okay, so today what we're going to do is we're going to talk about, we've talked about Ben Franklin discovering the positive and negative charges running through an electrical current. And so today we're going to talk about John Thomson's discovery of the electron. So John Thomson used a cathode ray tube. Okay, sorry. So he uses a cathode ray tube, and I know you can't see it very well, but you can kind of see it's this tube, and he fills it with inert gas. So an inert gas is, the word inert means non-reactive. So he filled this tube with a non-reactive gas, and he ran the electricity from the negative end, which is called the cathode, to the positive end, which is called the anode, through the gas. And what happens is the gas lit up kind of this pathway, which you can kind of see here. It lit up this pathway through the gas. All right? Now, so we're clear. You need to know Thomson's experiment for the test, all right? I can guarantee there'll be a question or two on my test, and there probably will be a question on the midterm, okay, from the county. So let's turn the page and see what happened when he did this. So remember, Thomson is trying to find out a little bit more about the atom. So what he did was this is Thomson's hand. No, it's not. I'm just kidding. He took a magnet and he put the positive end of the magnet, so the positive end of the magnet, toward the glass tube with the current. See, here's the current again. Right? Here's the current. And he put the positive end of the magnet toward the glass tube. And when he did this, he found that negative particles were pulled toward the positively charged end of the magnet, but no particles were pulled toward the negatively charged end. So what he did was he sees the negative particles pulled toward the positive end of the magnet. And then when he flipped the magnet around, nothing happened. It looked like the previous picture where the yellow line went straight across. And so he said, oh, look, negative particles are pulled toward the positive magnet, but no particles are pulled toward the negative magnet. So he had to figure out what that meant. And so, Thomson concluded that negative charges can be released from the gas. Look, here they are. They're being pulled toward the magnet. But that the positive charges can't be released. So when I flip the magnet over to the negative side, obviously those positive charges can't come, and for some reason, they can't come running toward the negative magnet. Why is that? So Thomson had to put together some sort of a model of the atom that would explain this. What does the atom look like? What is the atom like? That explains what I'm seeing. How can I explain what I'm seeing? So he put together a model, and a model explains his conclusion. And so his conclusion is that, so this explains his conclusions. So his conclusions, his plum pudding model, says that Thomson believes that the atom is a sphere, like a basketball, filled with positively charged gel, so all filled with positively charged gel, and that the negative particles are embedded in the gel, similar to raisins in plum pudding, and that when the magnet, the positively charged magnet, is put near it, these get plucked out and they head toward the magnet. But when the negatively charged magnet, when the positively charged magnet comes near it, the negative charged particles get plucked out and head toward the magnet. But when the negatively charged magnet comes near it, the gel cannot head over there because all of the positive charge is spread throughout the gel, so that wouldn't work. So the positive charges have to remain with the atom in the gel. And he called the negative charges electrons. So Thomson is sort of credited with finding the electron. Meanwhile, this is the model of the atom, this positively charged gel with the negative electrons in it that the scientists then were working on. Then a scientist named Rutherford, oh, star, 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 star. Yes, star, 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 very important, super important. Okay. A scientist named Rutherford, who actually was Thomson's student, he decided to do an experiment to test Thomson's model. And so what he did was he set up this experiment where, here's the experiment, where he shot positively charged particles, which are called alpha particles, And he shot them here from a radioactive source to this gold foil. So here come the alpha particles. And he was able to actually count the particles, so they weren't actually coming out like a flashlight. They actually were coming out like pew, 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 and he was able to count them. And by doing that, he was able to count how many particles were shot out. And the gold foil was 2,000 atoms thick. So how thick is that? That is about the thickness of aluminum foil. So it's not very thick, right? Okay, so he shot these positively charged particles out of this radioactive source, and he shot them toward the gold foil. Now, he said, if Thomson's model is correct, then these particles would have bounced back. So let me show you what he thought. He said, I think that if Thomson's model is correct, then what the foil actually looks like is it looks like these particles, these atoms are like this. They're like these stacked charged balls, right, of gel. They're all charged balls of gel, and they're stacked, so they have these curved edges, right? And then inside them are these embedded negative particles like this, right? So he said, if I send my positively charged particles headed over here, they're not only going to bounce back because positive repels positive, right? So they're not only going to bounce back, but they're going to bounce back at angles because they are round. These atoms are round, so they're going to go in like this and bounce back like that. They're going to go in like this and bounce back. A couple of them will bounce straight back, but the majority of them will go in like this and then go boop and bounce back at angles like this, right? Because these atoms are round. So his prediction, his hypothesis was if here's the hypothesis, if Thomson's model is correct, then my particles should go in and bounce back. All of them should bounce back. Most of them should bounce back at angles. But in fact, that's not what happened. What Rutherford actually observed was that almost all of the particles passed straight through and came out the other side, just like this. Almost all of them. Passed straight through and came out the other side. Once in a while, one came out like this, right? Once in a while. But for the most part, they all came out like this. Now, this reflective screen is set up here to deflect the alpha particles. And so as they were being shot out, pew, 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 they were showing up here, plink, as like little beams of light, little dots of light, plink, tiny little dots of light. So he could see where they showed up. So he was very able to see that the majority of the particles went straight through. A few bounced straight back, were deflected at angles, or bounced back at angles. So this is a very important experiment because he proved what his model was and his conclusions. So here it comes. Rutherford said that the atom is 99.999% empty space. Well, how he know that? Well, he knew how many atoms, how many alpha particles he actually sent out there. So he knew statistically how many were sent back, how many were sent off at angles. So he knew that 99.999% empty space meant that many went straight through. He also said that the nucleus, which is a word that he came up with, is at the center of the atom. So the other thing that he said was the nucleus is the size of a bee in the football stadium. So the football stadium was actually a soccer stadium, and it probably held about 500 people, so it was pretty small. But what he said was 200 atoms. So if I lined up 2,000 football stadiums and put a bumblebee, 2,000 football stadiums, and put a bumblebee in each one of them, and then I shot a bullet through all 2,000 of them, what are the odds that I would hit one of those bumblebees? Well, he said about 1 in 100,000, right? So he knew this statistically about how large the atom was compared to how large the nucleus was, based on how many alpha particles he sent into the football stadium. So he sent into the nucleus. So this is what he concluded. The nucleus is the size of a bee in a football stadium, and that the rest of the atom is empty space like the football stadium. He concluded that all of the positive charge and almost all of the mass is located in the nucleus. All right? So all of the positive charge and almost all of 100% of the mass is located in the nucleus of the atom. Now, in 1932, Chadwick discovered the neutron, so that's when that happened. And then Niels Bohr put the electrons into specific orbitals around the nucleus. So it was Niels Bohr who said, I think that, and proved actually, that the electrons travel in energy levels around the nucleus. So these are energy levels. And he said the energy levels have a specific amount of energy that the electrons need in order to be in that energy level. And in fact, he was correct. The electrons have to have a specific amount of energy to be in those energy levels. So he pictured that they were orbiting like planets orbiting around the sun. We now know that Niels Bohr was not correct. He is correct about the energy levels, and he is correct that they have specific amounts of energy, and the electrons have to have it. But what we do know is that they don't orbit like planets. We now know that the electrons are in something called an electron cloud, which is created because the electrons jump from one energy level, one of these energy levels, to another so rapidly and freely that they move around so much they create this cloud around the nucleus. In fact, they get energy just from light in the room, and they gain that energy jumping around, and they jump from little energy, but they do not orbit like planets. So that's the wave model. Now, the last thing that we want to discuss in today's information is something that you should be familiar with, which is protons, neutrons, and electrons. Okay, so protons have a positive charge, neutrons have no charge, and electrons have a negative charge. They are the 3 subatomic particles in the atom. The mass of the proton and the neutron is the same, but they have different charges. And so they have the same mass, though. So in nuclear chemistry, actually, it's possible to pull the positive charge off a proton, and then you end up with a neutron. So you pull the positive charge off and you end up with just the charge and then a neutron because the mass is the same. So the mass of an electron is 6/10,000ths of 1 AMU, so it's virtually weightless compared to a neutron or a proton. The AMU is the atomic mass unit for atoms or molecules, and that's because a gram is so small compared to atoms or molecules that we don't even use it. We don't use a gram because it's so small. So they created this atomic mass unit for atoms and molecules so that we don't have to use the gram because it's too small. And that's where we're going to stop today, and then you can look at the next module has your homework in it. Okay? All right, great.